Excellent morning to my Thursday morning darlings. We are going to continue with discrete math, and we're doing today many things binary. Let's take a quick look at the two problems we're going to be working with today. And I think that in the first case, it makes more sense that we look at the code first, and then after, I'm going to explain on the whiteboard what's going on so that you can follow the steps with me. And after that, we're going to talk conceptually about the second concept of binary trees. And then we're going to go over a reasoning of how to solve it. And then in the YouTube video, if you want to do it by code, there's also a little code explanation on how to do this. If you get impatient and you really need to be looking at this stuff before I get to it, you can look at the YouTube video straight up. But let's go to the study material to find the homework assignments. So we are in the fifth homework at this point, and we are going to be working with problems 1 and 2 today. The first problem says that we need to figure out how many calls to the routine B binary, the binaria. It's in the repository. I'll link it to you soon. We need to find the value 16 in an array that contains ordered integers from 5 to 54 in steps of 3. Okay, what on earth is an array? Let's look at this very briefly in a much larger font. Okay, so I am in Python. An array, effectively in Python, is going to be a list. Like I could make an array that contains the values 3, 7, and, 3, 6, and 12. I would also be able to make arrays that aren't sorted, and then I could just sort them to get them to go from the smallest value to the largest value in increasing order. And then if I would want this sorted thing to go in the opposite order, I could just index the whole thing the opposite way to get it from the largest to the smallest. So what we need to deal with the homework is a very specific array. We need ordered integers from 5 to 54. So let's work with that first. We want to start at 5. We want to finish at 54. And we want it to go in steps of 3. So there's a routine to do this in particular. I could say that I want my array to be all those x that are in the range that starts from start, goes all the way to finish, and goes in predefined steps. So this is a very easy way to create the data you are going to need for the homework. I'm going to take you guys a little screenshot so you don't get confused. So now it's really easy to know whether or not there's a 16 in here. I can just ask if there's 16 in A. There isn't. How does the computer know there isn't a 16 in A? It is going to search through the array. A stupid way to search would be, is the first one 16? No. Is the second one 16? No. Is the third one 16? No. Is the fourth one 16? No. Is the fifth one 16, etc. This would be very stupid. It's a little smarter if we take advantage of the fact that this whole thing is ordered, so that we would know that if we already got to 17 and nobody was a 16, then there's not going to be a 16. But that's still a bad thing, because if I want to know if 60 is in A, I would end up traversing the whole thing from the beginning to the end, trying to fix it, whether 60 is in there. So what we're going to be working with is a much smarter way to search. I've made a little animation, actually. I can see if the bot finds it. Yes, it does. So let's look at my little animation for a little while. So if I have my ordered array and I want to know if a certain value is in this ordered array, first I'm going to compare with the middle element. Then I'm going to discard the half that I don't want. So if the value I'm looking for is larger than the compared element, I'm going to discard the beginning because the beginning only contains the smaller ones. If the value I wanted is in fact smaller, I'm going to discard the larger ones. We're going to do this step by step on the whiteboard so that nobody gets confused. But as soon as you think you've understood it, you can just look at the GIF to make sure that you know what's going on in the GIF. So basically, to be able to do this, we are going to need a code because we need to look at the routine. I'm actually going to show you how to find it. So I'm just going to Control F right here and look for baby Nadia to figure out where that could possibly be. It doesn't say anywhere where that could be. So we're going to suppose it has to be in the repository. Let's look for binaria as such. Okay, búsqueda binaria. Okay, lovely. There's a little link here to bbinaria.py. So we're going to be working with this code. I'm giving you guys the direct link. And this code explains exactly how we are going to be searching. So when I receive the ordered data, I'm first going to check how many do I have. If I have no data, then the searched for element is not there because nothing is there. If I do have data, I'm going to look at the center position. That's going to be my pivot. If the pivot is the thing I'm looking for, I will return true because I have now found the element. If the searched for thing is actually smaller than the pivot, I am going to search again, but only in the front part of the array up until the position where my pivot is, recursively. If it were the other way around, the pivot was smaller than the thing that we were looking for, I'm going to be looking in the second half from the pivot onward without including the pivot because we already compared to it. So this is the code we're going to be working with. And this is where you're going to be putting your own values from what number up to what number in steps of what and what's the number you're looking for. Just a little precaution here in the steps of what. If the number that's your end is actually included in the list, you're going to want to put it here as a finish +1. Because remember that range only goes up to, but not including the last step. I'm going to copy this for you guys. So if you have these variables defined start, finish, and step, if it's not accepting your result as an answer, then you probably forgot to add a +1. But not everybody needs to add a +1 because if your end simply isn't part of the sequence taking into account the step, then this problem will never ever present itself. But let's go over this on in Python first, and then I'll do this on the whiteboard so everybody knows what's going on. So I have this code here. I'm going to take it in the raw. I'm going to copy paste the whole thing. Copy. And then I'm going to go to my idle to do pretty much the same thing that you guys are doing. In idle, I'm going to make a file. Nobody will copy paste anything in the shell. Nobody. Everybody will put this code in the file. Okay? Everybody. I'm also going to give it to you guys on Discord. And I just did that wrong. It didn't highlight. How on earth did I do it wrong? I thought I needed to type Python. Oh, maybe with Py it's better. Okay, there we go. So now I could add here the variables that I wanted. I could put from what value the homework was. Let's look at those again. We had 5 as my start. We had a 54 as my finish. And we had a step of 3, I believe. Yes, a step of 3. So now I would put here from where I was going. I put here the finish plus the 1, and I put here the step. And then what's the value that I am looking for? I am looking for a 16. So I am looking for a 16. All very lovely. I picked F6 instead of F5. So if I click F5, it's going to ask me to save this. I'm going to call it BB. I've apparently done this before. And now it says finish. Oh, because I wrote, I'm very Spanglish today. Hasta. Okay, so 16 is not in the array. This is all fine and mighty and lovely, except that it's not what the homework is asking you to do. It's not asking whether 16 is there. It's asking how many calls did we need to make. So how do I know how many calls we needed to make? I'm making one call right here. Then when I make that call, it can make other recursive calls. So how do I know how many calls I'm making? I could print something here. So anytime I start the routine, I would print out what are the values that I have and what's the value that I am looking for. If I run this now, I can see what's going on. First, it gets the whole array because I'm sending it the whole thing and it's looking for a 16. It compares 16 with the middle element. That ends up being the 29. 16 is smaller than 29, so all of this is discarded. And I'm going to make a second call using only this part of the data and again looking for the 16. So now we are in the second call. I'm going to compare 16 with the middle element, which is 17. 16 is smaller, so we're discarding all of this, and I'm making a third call with this data here. So in the third call, I have this data, and I'm looking for a 16. I need to take the middle element. It ends up being the 11. 16 is larger than the 11. So I'm going to discard all of this, and I'm only going to look with this stuff here. So I have only one element, and I'm looking for 16. This is going to be the pivot. It's smaller, so I discard it. So I have nothing left, and I'm looking for 16. When I have nothing left, I return a false. So really the only trick here is knowing that when I have an even number of elements, then my middle element is going to be the one right after the center. Why is it going to be the one right after the center? Because I'm taking the number of elements and dividing by 2. So 4 divided by 2 is going to be a 2. And the indices are, this is 0, this is 1, this is 2. So this guy is going to be the middle. This guy is going to be the middle, and this guy is going to be the middle. If I wanted to see what's the element that I'm using as a middle, I could also print that, but now it's dangerous to move the whole printout down here. Because if I move the whole printout right here, I can do this, I can entirely do this, but it's dangerous because now I don't see the last call anymore. I can see what's the value of n, but I'm missing one of the calls because the last call ended before I ever printed anything. So I need to make sure that whatever printout I add, it has to happen before any returns because returns make the routine stop. And if I want to know how many times was I in there, then I really need to print before I return. So I was there 5 times total, and that's my answer. I had to do 5 calls to figure out that 16 wasn't there. I'm going to take a couple of more screenshots for you guys. Then we're going to first make sure that you guys get the point, and then I'm going to go to the whiteboard and we're going to do a small example step by step to make sure that you're able to do this by hand if you ever need to. And why would you need to do this by hand? Option 1, you will need to explain it to another person. Option 2, somebody would ask you to do this in an exam. I won't, but somebody might. I have colleagues who have very different ideas on what's a reasonable thing to ask. So sometimes people make you do by hand things that make absolutely no sense to do by hand. So I'm going to want to show you how to do a thing by hand that makes absolutely no sense to do by hand. But we are first going to make sure everybody is getting the point. So if you have any trouble with Python, if it's giving you any error messages, please, please, please get a screenshot and put it on Discord so we can look at what might be the source of the mistake. Common mistakes in this homework would be not using a file, trying to put it in shell, because when you're copy pasting in shell, the part where the routine ends and other stuff begins, it often fails. Another thing that people very often do wrong is forgetting that range finishes not at the number you gave, but at one before the number you gave. So you really need to add the +1 to make sure that you have the correct values in your array. Because if your array is too short, the middle element will be different, and you're possibly going to get a different number of calls. So if we want to compare the code that was on the website and the code that I actually ran, I have added a print before the first return, and I have changed these values here. I put them here as variables, but you could just modify the values directly. Just remember to add a 1 to the finishing value. And please vote green when you have correctly graded problem 1 of homework 5. When I have at least 10 people who've actually been able to grade this correctly, then I'm going to go to the whiteboard to do the example by hand. But I'm going to give you guys a little while. And remember, any errors you get, copy paste or screenshot to the channel so I can look at it. Remember, if you don't have Python installed on your computer, you can use the online version. I'm going to link it again. You can even use that on a cell phone. Oh, great. I have spammers on Twitch. Blocking spammers. Okay, we have a bunch of people who are ready. So let's go to the whiteboard. I'm actually going to take a tiny intervention here, since we have spammers on Twitch, to address these spammers on Discord. Let me address this in Spanish, though. Hemos tenido algunas situaciones donde las cuentas de Discord de alumnos míos de semestres anteriores han sido comprometidas, que causa que tienen malware en su compu mandando mensajes en todos los channels. Si no quieres que te pase esta cosa vergonzosa, hay dos cosas que tienes que tomar en cuenta y es súper importante que si quieres ser un ingeniero que sepas hacer estas cosas. Uno es, no recicles la misma contraseña en dos apps, sitios web, servicios o más de dos. Siempre es una mala idea. Más bien usa alguna aplicación que te administre las contraseñas si no las acuerdas tú, pero nunca pongas la misma en múltiples, porque cuando le hackean a uno, digamos que le hackean a Instagram y tú tienes la misma cuenta en todo, pues entonces al rato van a estar en tu mail, van a estar en tu banco por internet, van a estar en cualquier servicio que tú utilizas. Entonces nadie necesita hacer un massive hack de Discord para comprometer cuentas de Discord si tú usas el mismo correo y contraseña en múltiples servicios. Eso es huevón y estúpido y no lo hagas nunca. Segundo, necesitas habilitar en cualquier cosa donde exista la opción la autenticación de dos pasos, el 2FA, que quiere decir que cuando tú entras a tu cuenta desde un nuevo dispositivo, nueva compu, nuevo teléfono, cambias de casa, tienes nueva IP, etcétera, te va a pedir no únicamente tu contraseña, sino también un código dinámico, un token que se genera típicamente en tu celular, y tú tienes que insertarlo únicamente esa primera vez. Le pones una tachita en la casilla de recordar el dispositivo. No lo hagas si estás en un ciber o en la casa de un amigo, pero hazlo si es tu propio dispositivo para que no te vuelva a pedirlo cada rato. Y eso lo que hace es que si una persona quien obtuvo tu contraseña de algún hack de algún sitio quiera entrar, no va a poder entrar porque no tiene acceso a tu teléfono. O sea, tendría que robar tu teléfono también para poder entrar a tu cuenta. Si tú proteges adecuadamente tu cuenta, teniendo contraseñas inteligentes, no recicladas, no pongas el nombre de tu novio número uno y un punto, o sea, un poquito más creatividad, por favor. No tienes que recordarlos. Hay muchísimas cosas que te permiten recordar contraseñas que son bastante seguras, y lo de autenticación de dos factores les ayuda en el sentido que ni siquiera si alguien hackea tu administrador de contraseñas van a poder entrar porque no tienen acceso a tu token. Entonces, eso sí es importante. Returning to the topic of binary search. So let's have a little array here, just a tiny little one. Not the same one we're working with in the code, just a smaller one to make life easier. So let's say I have here a 3 and a 7 and a 12 and a 30. That's a Z. That's not even a number. 32, a 41, a 47, and a 52. Now you're asking yourself, why would anybody want an algorithm to know whether there's a number in the array? Because it's stupid. You can just look at it. Imagine if this were a file that has thousands or hundreds of thousands of records of, let's say, credit cards that have been reported stolen. And somebody wants to use a credit card, and you need to check, is that credit card on the list reported stolen? So you're going to have to compare the credit card number with all of the ones that were reported stolen. And there's not going to be just a handful of them, there's going to be a ton. So we're just doing this with a small array. Of course, you can tell me whether there's an 8 or a 60 in this array just by looking at it. But in practice, in a practical application, you cannot just look at the data. So that's why we need a search algorithm. So we're going to do two searches with this one. First, I am going to search for something that's actually there. Let's search for 47 and see what the algorithm is going to do. So first, we tell the algorithm, I'm looking in this data for this number. And the algorithm is going to count how many elements do I have? 1, 2, 3, 4, 5, 6, 7. So n is equal to 7. If I take 7 and I divide it by 2 in an integer division, meaning discarding decimals, which is kind of like 7 divided by 2, taking the floor function, I'm going to get a 3. So which element is in position 3? This one is 0, this one's 2, this one's 1, 2, 3. This is the middle element. So my first comparison will be, is 47 32? it is not. Well, then next question, is it smaller or larger? It's going to be larger. So that means that I'm going to take the subarray from position 3 onward without including position 3. So in Python, that just means that I want to go from position 3 all the way to the end. Actually, position 3 plus 1, because I don't want the 3, because I already compared with it. 3 plus 1 all the way to the end. And now this is a recursive call, meaning I'm going to do the same exact thing, but now with less data. I'm looking for a 47 in this subarray. How many elements do I have? I have 3. 3 divided by 2, floor function is 1. Indices go 0, 1. So this one's my center element. I'm comparing, is 47 47? Hell yes, it is. On my second call, I return true. So the recursive call returns true to the main call that returns true to where I called this thing from. So that was 2 levels of recursion. My original call and a second call. Let's take a picture. Gonna be a horrible picture. Come on, phone, you can do this. Super dark. Okay, we're gonna take a picture by parts. I'm gonna take first a picture of calculations here. Then I'm gonna take a picture of the array. My head doesn't fit anywhere. The array here. And then no man, I clicked retake. Here. And a third picture of what's going on here. Use photo, send all this. So let's do a second one where I'm looking for a value that isn't there. So the first stage is going to be exactly the same. And the second one will depend on the value that we are looking for. So let's look for a 20. I'm looking for 20. First, I compare 20 with 32. It's smaller, so I'm only going to take the part from the beginning up to 3, not including 3. So I'm gonna get these. Then my middle element's gonna be the 7. 20 is gonna be larger than 7. So I'm going to search in just the 12. 20 isn't going to be the 12, it's larger, so I'm going to end up searching in an empty array, and the empty array means false. So then that false gets returned to the 12 one, which gets returned to the 7 one, which gets returned to the 32 one, and that's how I know that it wasn't there. So this is what's going on in binary search. If you guys would do me the favor of writing in your own words, Spanish or English, like a recap of what do you think binary search does and what is it for? Escríbanle, por favor, como mensaje directo al bot, a tu entendimiento a base de lo que acabamos de ver, qué es búsqueda binaria y para qué sirve, para que veamos en un tag cloud qué es lo que entendieron. Please. going to do it as well while you guys are doing it too. Let's find the box. This is the box. Oh, it's doing the thing again it was doing yesterday where it randomly erases itself. And then it comes back. I tried to debug it yesterday, like why does it blink on and off, but I really don't have any idea. Okay, I think we're fine. It's still blinking like crazy, but I'll fix it later. I wonder if it's because it's caching the, yeah, like I don't understand. Like it looks like when it's refreshing itself, it temporarily goes to John Travolta and then it comes back on the refresh. But it shouldn't. It shouldn't go through John Travolta. It should just be like the previous text and then it should be the new text. But not entirely certain. Not entirely certain. We'll try to figure it out at some point. Okay, so we have now a homework that we have actually responded to, and a second one that we're still going to work with today. So the second one, it also has to do with recursive stuff, and it's the same mathematical concept than here. We're going to be talking about binary trees, and we want to determine the minimum height we can achieve for a binary tree that is full and has 53 nodes. So there's a lot of new concepts here we need to learn. One is, what's a binary tree? When is it full? What's the height of a binary tree? And how do you achieve the smallest possible height? So let's go do this on the whiteboard. While John Travolta blinks back and forth. Let me actually reset it so it stops blinking. Okay. So the marvel of the binary search that we were just doing is that since we're always cutting it into half, we're actually going to end up, did it reset like it was supposed to? Come on, John Travolta. Be nice now. Ha ha ha. Let me try to fix this. I think I modified my Stream Deck buttons, but only for the simulation class. Yeah, that's the problem. I didn't modify them for this one. Trying again. There we go. It's kind of funny with the Stream Deck, if you have the same button in several different profiles, if you modify it in one, it doesn't modify in another. I would kind of like to be able to associate one single button. But what I was saying here before was that when I always cut the length of the array in one half on every step of the binary search, I'm going to end up doing a number of searches that's going to be a logarithm base 2 of how many values I had in the beginning. Because when I always cut into half and half and half and half, it's kind of like checking which power of 2 is this number. How many times can I cut it in half? So that's where the logarithm base 2 comes from. And this is a wonderful idea that when you want to do something with n elements, you don't have to make n comparisons. You only need to make log n comparisons because logarithm is much lower than the n itself. So we're going to be working with a data structure that takes advantage of this exact idea. Instead of storing the information in a list where we would have to do binary search in a list or an array, we're going to store it directly in a way that lets us do essentially the binary search without having to check which element is the center and which half I'm going to keep. So we're going to be making a structure where the numbers I want to store, they'll be arriving one by one. And we're actually going to be doing this next week as well. So I imagine someone sends me a sequence of numbers, 15, 3, 21, 34, 90, 24, 33, and 51. If I want to make a searchable structure of this, and I don't want to have to be ordering my array and whatnot, I can make a binary tree. I make a binary tree by taking the first number and putting it in a node. So the first number arrived and I put it in the node. This node, I'm going to call it the root because it's where the tree starts from. A little counterintuitively, my tree is going to grow downwards because this is the established convention. So just imagine it's an upside down world where trees go downwards. When I get a new number, I'm going to have a very simple rule. If it's smaller, I go to the left branch. If it's larger, I go to the right branch. And I'm only going to have two different branches, either left or right. I won't have more. This is why it's binary tree, because I have exactly two options. So the 3 arrives, it enters through the root, it's smaller, so it goes to the left. 21 enters, it's larger, it goes to the right. 34 enters, it's larger, it goes to the left, no, right. My left and right are so bad now because I'm trying to talk to you guys and I'm looking at the whiteboard too. It goes here, and I have to recursively repeat the same reasoning. In 15, it was sent on this side. And then from 21, it's sent again to the largers. So it's going to go here. Then I get a 90. It's bigger, bigger, bigger. It goes all the way down here. Then I get a 24. It's bigger, bigger, but then it's smaller. So it goes over here. Then I get a 33. Larger, larger, smaller, larger. It goes over here. And then a 51, larger, 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 and then smaller than this. It's going to go over here. So now this is a binary tree. The balls are the nodes, and whichever node does not have anyone hanging from it, those are leaves. So I have 3 leaves, 3, 33, and 51. I have internal nodes, this one, this one, this one, this one. They're sometimes called routers. And I have 1 root. Now, this tree is clearly not full because I have a vacancy. There's a node here that isn't present. There's a node here that isn't present. There's a node here that isn't present. And there's a whole subtree here that isn't present and a whole subtree here that isn't present. If it were full, then absolutely everybody would have 0 or 2 nodes. And technically, if I had the little red balls, it would already be full, even if it doesn't have the subtrees, but it wouldn't be minimal height full. So let's imagine here that we actually had some numbers, that this was actually a full one. I'm going to make up numbers that actually work. So we could have a 22 here because it's larger than 21 but smaller than 24. We could have a 92 here because it's bigger than everybody. And I could have a 17 here because it's larger than 15 but smaller than 21. So now I have a tree that's actually full. But let's look at what the height of this tree is. Height of a tree, it's defined recursively. The height of any leaf will be 0. So this one is a leaf. No, actually, it's going to be 1. Sorry. I always forget which one starts with 1 and 2. Okay, so this one's a leaf. It's at height 1. This one's a leaf. It's at height 1. This one's a leaf, height 1. This one's a leaf, height 1. And this one's a leaf, height 1. So all leaves have height 1. For anyone who's not a leaf, height is going to be the maximum over its children's heights plus 1. Max child plus 1. Height of max child plus 1 to be more precise. So this guy has 2 children. Their heights are 1 and 1. Maximum from 1 and 1 is 1. 1 plus 1 is 2. Here I have 1 and 1. The larger is 1. 1 plus 1 is 2. Here I have a 2 and a 2. The larger is 2. 2 plus 1 is 3. Here, this one's a leaf. So I have a 1 and a 3. Larger is 3. 3 plus 1 is 4. Here I have a 1 and a 4. The larger is 4. 4 plus 1 is 5. So the height of the tree will end up being the height of the root. Height of tree equals height of root in my horrible handwriting. Taking a picture of this. And yes, all of this will be in the exam. You're going to need to know what's a root, what's a leaf, what's a height. Okay, more or less. There we go. So now, it's super obvious that we now have here a tree that's higher than it needs to be. Because if 15 wasn't the root, if say, let's say 34 was the root, I would have a smaller height. Let's see what this thing would look like if 34 was actually the root. I'm going to try to lift it up higher. So I have the 34. From there, I would have the 24 hanging and the 90. And from there, the 51. From there, the 92. Then from the 24, I would have a 22 here, a 33 here. And then these missing guys, where do these missing guys have to go? Well, it kind of depends on which order would they have arrived at. We could make here a subtree that would actually hang from the, let's hang it from the 21. I'm actually going to hang it from the 17. So I'm going to put the 17 here. So 21 is going to be bigger than the 17, and then 22 is going to be bigger than that. And 15 is going to be smaller than the 17, and then 3 is going to be smaller than the 15. So now I've rearranged it a little bit, but I still have a height of 5. So it's a tree that contains the same data, differently ordered, but with the same height. I'm going to now make a tree with the same data that has a root 24. If I put the 24 in the root, I could put here, let's say I put the 51 over this side. Let's put the 34 here, put a 90 here, 92 here. Then I could put here, missing the 33 still, the 33 would have to go here. Then here I could have a, what's a good choice? With these numbers, there really isn't going to be a very good choice. Let's put 15 here, 17 here, no, actually 21 here. So I could put the 17 to the smaller, 22 to the larger, and the 3 here. And now I don't have 5 levels anymore. These are now only 4 levels. So I've actually made a tree that's a little less tall than the previous one. And now we need to start reasoning about what's the minimum height that we could have to allocate in the best possible way these numbers. The good thing is we don't actually have to think about the numbers. We just have to think about the shape of the tree. Because I could make a tree that has 4 nodes, that looks like this. Or I could make a tree has that 4 nodes that looks like this. So this one is the shorter one. So let's try to make a table of how short we can make the tree and how many nodes are we going to put in it. I'm going to put n for the number of trees, number of nodes, sorry, and h for the height of the whole tree. So if I have exactly one node, the height is going to be 1 because I only have the root. Then, if I have 2 or 3 nodes, it's going to look like this. This is not full because this guy's missing another. Sorry, doorbell's ringing. Sí, Elisa, sí. Sí, gracias. I am sorry I have to wash my hands and you guys have to listen to me because I didn't mute myself. Okay. So if I have 2 to 3 nodes in total, this would be what it looks like with 2. I can either hang one on the left or I can hang it on the right. And if I actually have the full tree, then it's going to be necessary like this. This is the shortest possible tree that has 3 nodes in it. This is another option, but this is not the shortest possible. So we're only interested in the shortest possible. We're minimizing the height. So this one's going to have a height of 2 because these are both going to have height 1. So this guy's going to have height 2. So if I add a new level to this tree, how many nodes am I going to be able to house? So if I increment my height to 3, how big can I make it? I could put nodes 4, 5, 6, and 7. So 4 to 7 gives me a height 3. If I add a new level, if I make the height 4, I could add 8, 9, 10, 11, 12, 13, 14, and 15. So from 8 to 15, I get height 4. We should be observing a pattern here in this table. 1 gives me 1, 2 gives me 2, 4 gives me 3, 8 gives me 4, or I could think 3 gives me 2, 7 gives me 3, 15 gives me 4. Mathematically, the important thing to observe here is how big are these layers. This one has 1 node, this one has 2, this one has 4, this one has 8. Next one's going to have 16, then 32, then 64, then 128, and so forth. So I don't have to draw, and I can continue this table here, because this is kind of like the power of 2, because it's directly the power of 2 that's going to be the next level. Because 1, that's 2 to the 0. This is 2 to the 1. There's, no, I'm writing them on the wrong side, sorry. This is the 2 to the 1, 2 to the 0. This is the 2 to the 1. This is the 2 squared. And this is the 2 cubed. So what I have here is the power plus 1, power plus 1, power plus 1. So this is 0 plus 1, this is 1 plus 1, this is 2 plus 1, this is 3 plus 1. So I know what this table is going to look like. I'm going to have a 2 to the 4th, which is a 16 here. I'm going to have a 5 here. Then I'm going to have a 2 to the 5th, which is 32 here. I'm going to have a 6 here. 2 to the 6th, that's 64. And I'm going to have a 7 here. 2 to the 7th, that's 128. And I'm going to have an 8 here. And then the end ranges, what are they? That's the number just before the previous one. So 3 before the 4, 7 before the 8, 15 before the 16. So this is going to be a 31. This is going to be a 63. This is going to be a 127. And this is going to be a 255. So just reasoning powers of 2 gives me this little table. And now we can answer your homework problem using this little table. So this is really marvelous. sending you guys a picture because now we can stare at this table to answer the homework that we're going to try to solve here. So in my case, it said, what's the minimum possible height for a binary tree that's full and has 53 nodes? 53 is a number between 32 and 63. And hence, I am going to necessarily need 6 levels because I cannot make trees that have less than 6 levels if I have to accommodate over 32 nodes, but no more than 63. So just look in the table, where does your number appear? And you're gonna be fine. We're gonna do the math in Python as well, but first just stare at the table, find your answer, put green when you've actually graded it correctly, and then I'll show you guys how to make this calculation in Python. Okay, I think we're good. So let's figure out how to do this in Python. So what we want to do is we want to reason out this math in this table, but with Python. So I would like to be able to know that if I need a certain amount of nodes, let's say 53, what's the height going to be? So I know I need a mathematical expression that does these calculations for me. I already know that I need the logarithm, and it's pretty obvious I'm going to need a rounding function because these are ranges. From 32 to 63, they all need to give me a 6. So I'm probably going to need either the ceiling or the floor to make these calculations. So now let's look at the logarithm of n base 2. Logarithm of n base 2 gives me 5 point something. And I would want the answer to be the same for all numbers from 32 to 63. All of these need to give me the same result, which needs to be 6. So how do I get all of these 3 to give me a 6? I will first need to round it down, get rid of the decimals, so that I get for all of these values exactly a 5. And then to that, I will add the 1. So now any value that's between 32 and 63 will give me a 6. So if I use this expression, I could make a little table for n in range, let's say from 20 to 50. I could print out 2 things. First, what's n, and then what's the value of this expression. So now I have a little table that says that if I have 20 nodes, I need 5 levels. And that's going to be true until I get 32 nodes. That's when I start requiring 6 levels, etc. And if I really wanted to, okay, now I'm forgetting that I'm not in an editor. If I really wanted to make it so that I don't print out all of the changes, I only print out when there's a, no, if I only want to print out when there's a change, if I don't want to print out when the value stays the same. So I could make a variable like, let's say, old height could be 0. Then I could make n go from 1 to, let's say 100 included. And then the new height would be the floor of the logarithm of n base 2 plus 1 if the new height is not the same as the old height. Now, what did I do wrong? Oh, I think I used spaces and tabs. This one's a tab. Then I want to print. Oh, my tabs look really weird. I want to print out both the n and the h. And then I want old to take the value of h. So now it only shows me when it changes. When I get to 1 node, I get 1 height. When I get to 2 nodes, I start getting 2 height. And then I remain at that height until 3. Then from 4 to 7, I'm at 3 levels. From 8 to 15, I'm at 4 levels. From 16 to 31, I'm at 5 levels. From 32 to 63, I'm at 6 levels. And then from 64, I don't see the end of it because I finished at 100, I'm going to be at 7 levels. So this is how I could make that same table that we have on the photo. So let me put this in Discord. I hate copying and pasting from the console because it adds me these dots. I don't want these dots. And these are actually spaces now, so I'm ruined. Maybe like that. Let me try copying it. Now remember, this is missing the imports. I should actually add them there because if you try to copy and paste this straight up, it's just gonna not work. From math, we needed log, and we ended up using the floor. That's a comma. I think that's a comma. Save. Take this whole thing and run it, and it seems to work. So that's how we can answer the second homework. And apparently 18 people have been able to do this. So now if you're very eager to save time for the coming weeks, because other courses of yours are getting heavier and heavier, you should be able to do the third question based on what we were talking about just now on the whiteboard. If you understood the smallers go left and largers go right thing, you can already do question 3. But that's how we're going to start next week because I don't want to overwhelm anybody. So we're going to do that next week, then a tiny other code as well, and then the question 5, but the question 5 is in a separate video, which is here. It also has to do with trees, but those trees are not going to be binary anymore. They're going to be spanning trees. So that would be what I really wanted to do with you guys today. I'll try to debug the flashing Tron Travolta to try to figure out why is he doing that. And I've also been informed by my boyfriend that there's a weird voice delay in Twitch. So I'm also going to make some settings changes in Twitch. If you got confused, then you need to go through this material again. In 1.5 hours at noon, I'm going to stream the same stuff again in Spanish, and you are welcome to join. I'd like to remind you that you can practice the exam online. And with what we saw today about what's a root, what's a node, what's a leaf, what's a height, you can already answer a bunch of more questions in the final exam. So that should be helpful. And I will be pending on Discord in case any of you need help. We should all at this point have a total of 44 points in the homework. We can go look at those points and see if that's actually true. There are a bunch of people with 44. Yeah, we're doing decent. We're doing decent. In your group, we have 43% of the people started the fifth homework, and they've done half of it on average. So we're doing pretty well. I'm hoping that we're going to have similar success here in the afternoon group. But thank you guys for your attention. I'm going to give you the link to the recording in a bit, and I'm going to mess with all those settings that I just mentioned, so we will have a smoother experience next week. Bye.